In this video, I'm going to talk about the solutions to the questions that I posed for the midterm one review. Okay, so I'm going to talk about the solution one by one in the following video. So this video may be longer because we have talked about all solutions for all questions. Okay, all right. Let's start with first question for the midterm one review. So the first question is about the matrix product, matrix determinant, matrix inverse, eigenvalue, eigenvectors. Okay. All right, so I'll give you two matrix. A is a 3 by 3 matrix. It's 3, 1, 2, 2, 1, 3, 1, 2, 3. Okay, so this is the matrix I have for A, and B is 1, 2, 3, 1, 2, 3, 3, 2, 1 is 2 by 1. Means two rows, 3 columns. Okay, so first of all, what is A times B? The product A and B, A times B. Because if I remember, I mentioned A and B, right? This is, let's say, A m times n, that's B n times P. So this number must be equal in order to compute the product. So here I have A is 3 by 3 and B is 2 by 3. So apparently those numbers are different, so they cannot do a product. So the A times B is not well defined because A is 3 by 3, B is 2 by 3. Okay? And B times A is well defined because 2 times 3 and 3 by 3, of course, they will be equal, all 3. Alright, so the product can be computed by this way. If you remember how to compute that, is the first number over here is computed by the first row times first column. What I mean by time, I mean entry-wise product, and then you compute sum. So it will be 1 times 3 plus 2 times 2 plus 3 times 1. So it will be 3 plus 4 plus 3, which is 10. Okay, so this will be the same with this guy times this guy. Okay, the first row times second column of A. Okay, you do the same way for the first row times the last one for this value. Then you can compute the similar for the second row, all the number computed in a similar way. So the final answer to this question will be 10, 10, 16, 14, 10, 12. Okay. Alright, next is about the eigenvalue, eigenvectors for matrix A only, because eigenvalue, eigenvector only apply to square matrix, which means I must have A n times n, so this must be equal, otherwise I don't have eigenvalue, eigenvectors. Okay, so how do I compute eigenvalue, eigenvectors? So this is how, first let's compute eigenvalues. So the eigenvalues are computed by solving the determinant of A minus lambda I is set to be 0. Okay, this is also called a characteristic equation. Okay, so you compute the determinant of A minus lambda I, and you set to be 0, and you solve for the solution of lambda. Those will be your eigenvalues. Okay. Alright, so this will be if I put the A inside, so A is 3, 2, 1, 1, 2, 1, 3, 1, 2, 3. So I put in those A and then minus lambda I. You can equivalent to this. So if it's the same as determinant of lambda I minus A is set to be 0, because that's the same. Okay. Alright, when you do that, I just use the determinant A minus lambda I. So I have this 3 by 3 matrix. When you compute a determinant, what you do is you just pick a row or any column. You compute the you reduce this 2 by 2 matrix. You have what we have. This is same. If I use the first row, let's say example, I try to compute it. So it will be the remember this will be the minus 1 for this first entry. Let's start first entry over here. Okay. 1 plus 1, because on the first row, first column, this is 1 plus 1, okay, and I type whatever entry I have here is 3 minus lambda, okay, then I have remaining is it will be the determinant of this. You remove the row and the column this entry is on, so this remove this row, this column, so we have this 1 minus lambda, 3, 2, 3 minus lambda, and plus second one for this second entry. Let's move to the second entry over here. Plus is minus 1 is 1 plus 2, because I have first row, second column, this is 1, 1 and 2. That's where this 1 and 2 coming from. It's first row is 1, second column is 2, okay? Then I have repeated whatever value I have here. This is 2, I copied over here. Then I have to delete the row and a column, and then remaining is 2 by 2 matrix. You take a gradient, determinant of that is 2, 3, 1, 3 minus lambda. Okay, right, let's do the last one. The last one will be plus, again, -1 is 1 plus 3 because it's first row, last column. Okay, so 3 is the third column basically, right? Time 1 is I repeated 1 over here, so the remaining one will be delete the row, delete the column. I have remaining one will be the 2 by 2 matrix will be 2, 1 minus lambda, 1 and 2. Okay, then this one you set it to be 0, of course. It anyway, if you do all, if you just try to compute a 2 by 2 matrix, determine 2 by 2 matrix for all three, and when you move together, you actually get this. It's actually lambda negative lambda cube plus 7 lambda squared plus minus 4 lambda plus negative 12 is set to be 0. And of course, I can put negative sign on both sides, which give us lambda to the cube minus 7 lambda squared plus 4 lambda plus 12. So this one can be written as factored as lambda minus 6 times lambda minus 2 times lambda plus 1. Okay, so this can be a little bit challenging. So typically, I don't ask you to actually compute the 3 by 3 matrix. It's a little bit difficult to compute all 3 eigenvalues. For 2 by 2, you should be able to compute the eigenvalues, all the solutions fairly easily. Okay, for this case, I have 3 eigenvalues. There are lambda 1 is 6, lambda 2 is 2, lambda 3 is -1, because I have either of these 3 terms be equal to 0. Either lambda minus 6 is 0, or lambda minus 2 0, or lambda plus 1 0. Then make sure that this is 0, right? So I have lambda 1 is 6, lambda 2 is 2, lambda 3 -1. Alright, now let's move to the eigenvector. Okay, so for each eigenvalue, we can find this eigenvector. Okay, so let's start with the first eigenvalue, which is 6. So for lambda 1 being 6, okay, let's assume that it's eigenvector given by x1, x2, x3. So we must have a 3-dimensional vector, okay? Then what I have is, oh yeah, I can have this. According to the eigenvector, I have a lambda is, ax is lambda x, basically what that means. Okay, of course here's lambda 1, so I do ax equal to lambda 1x. So I can sort of write this one as, I plug into x, a and x. Okay, a is 3, 2, 1, 2, 1, 3, 1, 2, 3. X is already defined over here is x1, x2, x3. Number 1 here is 6. Okay, and of course I multiply x, which is x1, x2, x3. So I end up having 3 linear equation over here. Okay, so if I clean a little bit, so I can find a solution will be x1 is 1, x2 is 1, x3 is 1. So you don't have unique solutions. They have many solutions. So you can have 2, 2, 2. That's the same. Okay, so you just find a one solution to this one will be okay. That's the eigenvalue. Okay. Okay. I don't talk about solution to this linear equation. You can actually find it very easily. So for lambda 2, which is 2, we can follow the same way. We can define, let's say we can have x be the eigenvector, which is x1, x2, x3. We again can plug in which is ax equal to lambda 2x. Of course, lambda 2 here is 2. It's not 6 anymore. So just rewrite this one as an equation, linear equation. So I can compute the solution. One of the solutions is -7, 1 of 5. So this will be eigenvector. Similarly, for lambda 3 being -1, follow the same way. So I don't want to talk about too much detail about this. What we end up having is this type of equation will be ax3 equal to ax, which is lambda 3x. So you plug in the a and you plug in your x and lambda 3 -1, so you actually have 3 linear equations, and you can compute one solution. So only one solution will be fine. Okay, you have infinite solution for this 3 equations because they're actually one redundant one. Okay, so you can compute 2, -5. 2 is eigenvector. Actually, you can actually verify 4, -10, 4 is also like any scale. You scale it by a fixed number is still a solution to it. Okay, so once we have this one, we actually compute all the eigenvalues and eigenvectors for the matrix A. Okay, all right. Now let's compute the determinant and inverse of A. So the determinant, as I mentioned to you, determinant is computed by this. You can pick any row and any column. Okay, what you do is for each entry, let's say we start with the first row only. So we just have to go through each entry in this row or column, for example. So I should go to each one. Okay, right. So let's start with the first one, number 3. Okay, so first you put a number 3 over here, then you put -1 to power. So this power is determined by the number of row, the number of column that this entry is on. For example, this entry is a first row, so you put a 1, first column, and you put another 1. It's a 1 plus 1 basically. So 1 plus 1. So these two numbers are coming from the number of row. This number of row plus the number of column that this entry is on, basically. And then you delete it. Then you have you reduce the dimension of this matrix A by 1 row and 1 column. You actually reduce 1 row and 1 column. The row and column that is try to reduce the row and column this entry is on. For example, this 3 is on the first row, so you delete the first row, and the 3 is on the first column, delete the first column. You end up only have these 4 numbers. You have 1, 3, 3, 2, 3. So that's the 2 by 2 matrix, right? You compute a determinant. So for 2 by 2, you can know that determinant is just the product of diagonal entries minus the product of the off diagonal entries. You know how to compute that. Okay. The similar principle apply to you do the plus, of course. Similar principle apply to all other entries. You do the same way. 2 times minus 1, 1 plus 2, because this is on the first row, second column, and then you delete the rows entry is rows column that this entry is on. So you delete the first row, then the second column. You end up having 2, 3, 1, 3. Okay. Similarly for the last one, which is 1. Okay, you do the same way. Okay. So after you do the computation, you actually can compute the determinant, which is -12. Okay, all right. So the inverse, there are 2 ways I talk about inverse. Okay, so I'm just using one way to compute the inverse. Okay, so A inverse is equal to 1 over the determinant of A times the cofactors of each entry. So difference is over here. Pay attention to the cofactor. Cofactor is something exclude those numbers. So the remaining part will be the cofactor. This will be just the cofactor for, let's say, is C11. You compute this is the cofactor first one. This is cofactor of C12. This is cofactor of C13. Okay, of course you can compute C21, C22, C23, and C31, C33. Okay, this is called cofactors. So what we pay attention to, this is C1. We just have computed 9 cofactors. For each entry, you compute cofactors. Okay, C11, C21, C31. So this is not. I want to say this is not C12. Okay, it's not a C13. It's basically you do you switch from the row to a column. Basically, the first row will be the column will be C11, C12, C13, and C21, C22, C3, C31, C32, C33. Okay, so since the determinant already computed over here is -12, just plug in the numbers. -12. Okay, I don't want to compute each one. You can compute each one if you want. Okay, so which basically means I can actually compute all the stuff that I want. Okay, so all the 9 numbers. Okay, right over here. Okay, then you plug in the numbers. Then you just, since they have negative sign over here, you actually can move the negative sign inside. You put negative on each entry. You actually flip the sign, each entry inside the matrix, and you make this positive. Then you have this sort of inverse. Okay. All right. The next question about the eigenvalue, eigenvectors associated with A squared. Okay, so if I know an eigenvalue of A, actually I can compute the eigenvalue eigenvector A squared pretty straightforward. Okay, I don't have to compute the matrix first, then write using the way I mentioned over here to compute eigenvalue, eigenvector, because eigenvalues and eigenvectors of A squared actually are related to the eigenvalue and eigenvector of A. So which means I don't need to compute those one by hand by following the previous ways. I actually can find a relationship. Based on relationship, I can tell. Okay, so if lambda is eigenvalue of A with associated eigenvector x, then I can have ax times lambda x. That's the definition of the eigenvalue, eigenvector. If I multiply both sides on the left hand side of this previous equation by a, so I have here is a squared, right? A squared pi times x. And this guy is, I can actually swap the lambda a because lambda is scalar, I can move the front. And a times x again, because a times x is equal to lambda x, so it's lambda times lambda x, which is lambda squares. If you look at this, I have actually a squared x lambda squared x. So what it means is this guy will have eigenvalue which is lambda squared. Eigenvector is just x. Okay, which means I have lambda squared is eigenvalue of a squared with x being associated eigenvector. So if, for example, for the original eigenvalues for a, for example, I have eigenvalues are 6, 2, -1. Okay, so I have here eigenvalues are 6, 2, -1. For the eigenvalue of a squared, you just do the square of each one. So you have 36, 4, and 1. And the eigenvectors, they're not changing, they're the same. So just copy them down over here. That's the original corresponding eigenvectors. Okay, all right. So the next question is a little bit more complicated. It's about a matrix diagonalization. Actually build on what I mentioned in the previous question. Okay, all right. So let's talk about how to do that. So the question is, if I give a matrix A which is 1, -2, -2, -2, I want to diagonalize this A into this AX times lambda times X inverse. So this X, this lambda basically means is a kind of diagonal matrix. Okay, if you remember. If you don't know how to do that, actually, you can read my previous video on how to do the diagonalization. Okay. Okay, so if I do eigenvalues of A, so how to do that? Before I do that, actually, we know the X and lambda actually composed of the eigenvalues and eigenvectors. We just need to first compute the eigenvector first. Okay, to compute eigenvalues is, again, as mentioned in the previous problem, I have to compute the determinant A lambda is set to be 0, which is a characteristic equation for this A raised to the A. So this is by 2 by 2 matrix, so the computation is quite straightforward. So 2 by 2, you compute determinant of 2 by 2 matrix, which is product of the diagonal entry minus product of diagonal entries. So which is being given by this. You just clean up a little bit, so you have lambda squared plus lambda minus 6 equals 0, which means I can write this one as lambda plus 3 times lambda minus 2 equal to 0. So I have two solutions. One is -3 and one is 2. Okay. Alright, so for each of the eigenvalue, I need to compute the eigenvector. Okay, so follow the same way I mentioned in the previous problem. If I let x1, x2 be the eigenvalues, I can kind of write this as a times x equal to lambda 1 times x. So I just replace this a by the actual values, and x by what we defined over here, and lambda 1 by what's the value is -3 over here. So I can compute the eigenvector, which is one eigenvector is 1 and 2. Okay. Similarly, for lambda 2 is 2, if we assume x1, x2 being this column, this vector being eigenvector for this eigenvalue, so I can still write this as sort of ax equal to lambda 2 times x. Just plugging all the number for a, for x, for lambda 2. So I can also compute this -2, 1 is the eigenvector. Okay. Once we have the eigenvector, we actually can construct the lambda, which is just that we put the eigenvalues on the diagonal entries of this the same size. If this is 2 by 2, for example, this lambda is also 2 by 2, which means we put eigenvalues over here. And then for x, we just build this eigenvector. We build x, put the eigenvector over here. So the sequence matters. So if I put an x3 over here, I must put the first column, okay, over here, first column. This is in column, not in row. First column, which will be the eigenvector for this guy, the first value we put over here. For -3, for example, the eigenvector will be 1, 2, so I put a 1, 2 over here. The second one, eigenvector as a vector for the second entry over here is -2, 1, so I put it as the second entry over here. Then I will have this relationship like a will be equal to x lambda times x inverse. So x will define it right over here, lambda defined over here. Okay. Of course, you can swap the order. If you switch the order 2 and the -3, you must switch the order of these two columns. That's true as well. Okay. All right. So let's go to the next part. Is about the vector operations applications. Okay. It's about a vector operation. Okay. So There are a couple of questions. Let me go over one by one. So the first one is if I give you two vectors A and B, there's 2, 0 and 0, 2. So we talk about a vector plus. Okay, vector plus is you just do entry-wise plus. Okay, 2, 0 plus 0, 2, so you have a 2 and a 2 because you do entry-wise plus. You do 2 plus 0, which will give us 2, and 0 plus 2 also give us 2. Okay, the matrix dot product A dot A. Okay, A dot A is you do sort of the entry-wise product and you do the sum. Okay, so for A times A, if we have here is like 2, 0 times 2, 0. You do entry price 2 times 2 plus 0 times 0, you give 4. So A dot B, you do still do entry-wise product, but you do A times B. So we have 2 times 0 plus 0 times 2, which give us 0. Okay, so how about A cross B? The cross product here is not well defined because A cross B only applies to 3-dimensional vectors. Okay. The second question is the projection. Okay, so if I give you A vector which is 1, 2, 3, B vector is 2, 3, 4. So the question is to find the vector that results when we project A in the direction of B vector. Okay. If you remember what I mentioned in the class about the projection, okay, so first of all, the length of C will be just equal to A dot B and divided by B magnitude. Okay, A dot B is already computed over here. So dot product is just a computer entry-wise product, and you compute the sum. So it will be just 1 times 2 plus 2 times 3 plus 3 times 4. Okay, and divided by the norm, the magnitude of this B is square root of the square of each entry. 2 squared plus 3 squared, 4 squared, take a square root. So this gives you something like this. So when you have that one, what you do is the C is be given by the magnitude of C itself times the direction, right? Okay. So the direction will be just the B vector divided by B vector self divided by unit B the magnitude, which will give a unit vector along the direction of B of B. So will be this already computed norm, the length of C will be just 3.7319, and you time the B vector divided by its magnitude. Okay, 2 squared plus 3 plus 4 squared is 2, 3, 4. Okay, after you do that, you get this. Also, you can say I just C is equal to A B divided by B. You can also do this time B. That's it. You can also compute this directly. It should give you the same number. Okay, right over here. Okay. So last question is about computing the cross product. Again, cross product only applies to 3-dimensional, so only 3D vectors. So which means you have 3 entries in your vector. Okay. So let's say if I have A and B, so A and B actually defined over here the same A and B 1, 2, 3, 3 to 4. Okay. Alright, so to compute the cross product of A cross B, what to do, the first row is always I and J and K, okay? Then whatever you have for the A vector, the numbers will come to the second row, and then the B comes over here at the last row, okay? Then you compute the determinant. You typically do the first one, using first row to compute that. So what you do is, you do -1. You can also move this. I move this toward the end, but you can also do this as very beginning. Okay, it's I times -1, 1 plus 1. Follow the same principle. For this one, you put it over here. So you do -1 times 1 plus 1 because it's on the first row, first column. Then you do a 2 by 2 matrix. Okay, determine 2 by 2 matrix. This 2 by 2 matrix is obtained by removing the row and the column this I is on. So which means I delete the first row and the first row and the first column. So I have 2, 3, 3, 4. Okay. The same you can do is I can just move over here, make it consistent. So J times -1, 1 plus follow the same way. Okay. So you delete the first row and the second column. You actually have 1, 3, 2, 4, 1, 3, 2, 4. And don't forget to have -1, 1 plus 2 because I have J's on the first row and second column. Okay. And this one plus K times -1 and 1 plus 3 because I have first row, last column. And then delete first row and last column, and remaining term entries will be 1, 2, and 2, 3. Okay? Then just clean up a little bit. So I have -1 times I plus 2 times J plus -1 times K. Okay? That's what we have. So you can also write this as vector. Okay? Vector means whatever comes from the I will put as first entry. What comes in front of this J will be the second entry. Whatever comes in from the K will be the last entry. So I have a vector will be -1, 2, -1. Okay, this is how to compute the cross product. So in terms of B cross A, if you remember in the class, I mentioned B cross A is just a negative of A cross B. So you can use the property directly telling me that this just flip the sign of the vector. It's a 1, -2, 1. Of course, you can also compute the B cross A by using the same way I did over here. You still put the I and J and K as first row. This time you put a J. Okay, you put a J here as your second row. B as the first row. Whatever number in B as the second row because B comes first. Then you put the A, whatever numbers in A will be as the last row because A vector comes as the second one in your cross product. Okay, then you can do the same way, then you should get the same result over here. Okay, that's all for the midterm review solutions.